All right, so in this section, we're just going to take a look at how we can use these experimental designs and studies wisely and effectively. So at the end of this, you'll be able to understand when you can use causation and when you can establish cause and effect, and when you can be able to understand when you can use inference to a larger population. So that's defining the scope of inference, and how do data ethics apply whenever we're designing studies. All right, so we want to make conclusions beyond the data that we gather. So let's just take a look at this first scenario. The U.S. Census Bureau carries out a monthly current population survey of about 60,000 households. Their goal is to use the data from these randomly selected households to estimate the percent of unemployed in the population. So what is key here? All right, what is key here? Number one, the individuals were chosen at random. So what does that allow us to do? That allows us to avoid bias. So that means we're not overestimating or underestimating the amount of households that are unemployed in the population, and gives us trustworthy results about the population. So when we have random selection, we are able to apply what we get from the sample to the larger population. However, since this is just an observation, there's no cause and effect here. All right, so let's take a look at the second one, sleep deprivation. Scientists performed an experiment on randomly assigned 21 volunteer subjects to one of two treatments: sleep deprivation for one night or unrestricted sleep. The experiments hope to show that sleep deprivation causes a decrease in performance 2 days later. So that's like if you're a sports person, they always say it's not the night before that you need a good night's sleep, it's the night before that you need a good night's sleep. So they were checking to see if this was in fact true. So what's key here? What kind of inference can we make? Number one, the subjects were randomly assigned to the treatment. When we have random assignment to the treatment, we can make inference about cause and effect. However, we cannot make, in this case, a scope to the larger population or inference to the larger population, because they were randomly assigned, but it doesn't say they were randomly selected 21 experimental units. They were 21 volunteers. So the only person that we can make inference about is those specifically in the study. All right, so we just talked about this. Now, in this section, we're just going to talk about, we need to be able to answer the question on what type of inferences can be made. All right, so can we make an inference to the larger population, and can we establish cause and effect? Randomization, randomly assigning and randomly choosing our sample will help us to decide which type of inference, if any, is appropriate. All right, so let's take a look at random selection. If you have random selection for your experiment, we can make inference about the larger population, not just the sample that was selected. When you have random assignment in the experiment, we can now make inference about cause and effect. So you're going to want to read the question very carefully to see if they talk about randomly selected experimental units and randomly assigned treatments. All right, so random selection, you're randomly selecting. You can make inference about the larger population. Random assignment, that's where you can do cause and effect. Just make sure you understand the difference between the wording. Read the questions carefully to see if they discuss random selection and random assignment. All right, so let's just take a look at a couple of examples. So what type of inference can be made from a particular study? So this is saying, can we establish cause and effect? Can we make it to the larger population? It depends on the design of the study. Your goal is to make well-designed experiments. In order to have a well-designed experiment, you want to make sure you're randomly assigning the individuals to the treatments. However, the tricky part is here that most experiments don't always select experimental units at random. And the reason for that is it's difficult to do that. People might actually not want to participate. For example, I know that a lot of universities, and a lot of like clinical drug trials, you have to volunteer to be part of the experiment. So they're not selecting them from the larger population. They're just selecting them from the volunteers, or they're just volunteers. This limits the experiments to the inference about cause and effect. So usually we can only say that the cause and effect or the treatment worked for those particular people in the experiment. So that can be a little bit tricky. Observational studies, when we do an observational studies, they don't randomly assign individuals to groups. We're literally just looking at something that happened. We're not applying a treatment. So with observational studies, there's no cause and effect. All right. We can only potentially apply it to the population at large if they were randomly chosen to observe. All right, so here's just a little chart right here in order to decide, can we make inference about the population? Can we make inference about cause and effect? So were they randomly assigned to groups and were they randomly selected? Then yes, you can make inference about the population and cause and effect. If they were randomly assigned but not randomly selected, you can make inference about the population. You cannot make inference about the population, but you can do cause and effect because they were randomly assigned to the groups. All right, so if they were not randomly assigned, but they were randomly selected, okay, since they were randomly selected, we can do inference about the population, but cause and effect, no, because they were not randomly assigned to the treatment groups. All right, and then the last one, if they weren't randomly assigned, they weren't randomly selected, you should just throw it out and start over. Okay, so just make sure you understand that chart and be able to very carefully read a study. And this is just as you grow up and you might do some research about, whether or not you want to take a certain drug. When you read the studies, you really want to read the experiments and check and see, were they volunteers? Like, were they randomly assigned? I'm sure they were randomly assigned, but you want to really dig into that study and see if it actually applies to you. Okay, now, oftentimes we can't do an experiment, and this is dealing with ethic reasons, which we'll talk about later, but we can use some other criteria to establish causation. So sometimes we can't do an experiment if it's unethical. So what are some ways we can say, okay, we can still establish cause and effect if these 5 things are true. Number 1, if the association is strong, the association is consistent, larger values of the explanatory variable are associated with stronger responses. The alleged cause precedes the effect in time, and the alleged cause is plausible. All right, so we'll go over what all these mean for a specific example. So let's just think about, let's say we were doing a study, an observational study, on the relationship between smoking and lung cancer. Now, obviously, you can't create an experiment with this because you can't force people to smoke and then see whether or not they get lung cancer. That's not going to be very ethical. But take a look at the next slide, and it's going to address these 5 characteristics to say, hey, we can actually, in this case, use an observational study to establish cause and effect. Okay, so let's see if smoking and lung cancer meets those 5 criteria. The association between smoking and lung cancer is very strong. So if they looked at everybody that had lung cancer, maybe they said, 75% of the people that had lung cancer also smoked. And that is consistent over a course of time. So that association is consistent. So that's basically like saying there were many, many observational studies with many, many different kinds of people in many countries linking smoking to lung cancer. So it wasn't just one study. Consistency means it's similar among all groups, among different countries. All right, so that helps to make that association stronger. That reduces the chance that some other variable specific to one group or one study explains the association. So if we were just looking at the United States, then we couldn't necessarily, say that smoking causes lung cancer because maybe it was something specific in the United States that associated lung cancer with smoking, but since it was consistent across many populations, many different types of people, that shows a strong association that is consistent. People who smoke more cigarettes per day or who smoke over a longer period get lung cancer more often. People who stop smoking reduce their risk. Lung cancer develops after years of smoking. So the number of men dying of lung cancer rose as smoking became more common with a lag of 30 years. So that's about the effect in time. Lung cancer kills more men than any other forms of cancer. All right, so that's rooting for the strong association. Now, experiments, whether or not some people might think this is ethical, with animals show that tars from cigarettes smoked do cause cancer. So they did do an experiment. They just did it on animals instead of humans. The evidence for causation is overwhelming, but it's not as strong as evidence provided by well-designed experiments. Okay, so, but obviously this isn't necessarily an experiment that you can do. It would be very unethical. So there are some challenges in establishing causation whenever we're looking at observational studies and well-designed experiments. So a well-designed experiment tells us that changes in the explanatory variable cause changes in the response variable. So if I did take those animals and expose them to various amounts of tar for various amounts of time, that does cause a change in the response variable, or the how much lung cancer maybe the animals got. The lack of realism can limit our ability to apply the conclusions of an experiment to the settings of greater interest. Okay, so lack of realism. So once again, that's like, you know, we don't have a real life place where we can actually test, give people, have people smoke cigarettes for a certain amount of time and then see, you know, the varying rates of lung cancer. So in some cases, it isn't practical or ethical. Okay. So one way would be texting and driving. Does that increase the risk of having an accident? No, but you could go through those 5 different things and look at all the data. Does going to church regularly help people live longer? You can't really force people to go to church. And does smoking cause lung cancer? Like, obviously, you don't want people to force people to smoke. We can't do an experiment because we don't want people to text and drive. We can't force them to go to church or smoke cigarettes. So it's sometimes possible to build that strong case for causation in the absence of experiments by taking a look at all of the data from those observational studies. So complex issues such as data ethics arise when we collect data from people. So there are some basic standards of data ethics that must be obeyed by all studies that gather data from human subjects in both observational studies and experiments. So number one, just know that all experiments that involve humans must be reviewed in advance by an institutional review board charged with protecting the safety and well-being of subjects. So if they're testing a new drug, they have to get it approved that they can test it before they can just say, hey, come here, let's randomly test my drug. We don't know what's going to happen to you. All right. They are making sure that it's safe. All individuals who are subjects in a study must give their informed consent. So that's just signing something to say, hey, yes, I know the side effects, but I still want to be part of the study. And the individual data has to be confidential. So only statistical summaries for groups of subjects may be made public. So that's like saying when we did a study of 15,000 people, 12,000 of them had increased lung cancer. All right, so here's your basic summary. So inference about population requires that the individuals taking part in a study be randomly selected, and a well-designed experiment that has random assignment of treatments is cause and effect. So lack of realism in an experiment can prevent us from generalizing the results, such as texting and driving. In the absence of an experiment, sometimes when we have a strong association that's consistent and there's a clear explanation for the link between the explanatory and the response variable, we can sometimes use observational studies, but we'd have to carefully look and make sure that the possible lurking variables aren't accounting for that response in the response variable. So studies involving humans have to be screened in advance by the institutional review board, and they have to give informed consent before testing any, usually drug or something like that. And the results that they get from the study must be confidential.